Siyuan is a research scientist at Beijing AI Institute for General AI, BIGAI, where he directs the Center of Embodied AI Research. His current focus is on developing generalizable models for general purpose robots. So, Siyuan, would you come to the stage?
Start?
Yes,
Start.
please.
So thank you for the workshop today. It's early and we have some technical issues, so I will speed up for several minutes maybe. And my name is Siyuan, and today I'm going to talk about some of our recent work in how to build interactable digital twins of articulated work. And I will share some of our recent works from two perspectives, reconstruction and projection. So first thing is, here is an very brief introduction about myself. So I graduated from UCLA in the 2021, and then I work at the Beijing Institute for General Artificial Intelligence. And my long-term goal is to do the 3D thing understanding for the general purpose agents and robots. So back to the topic today, and we are interacting with articulated objects everywhere and in our daily life. So, for example, if we are like opening a microwave and refrigerators or opening a drawer, so we are interacting with articulated objects at any minute. And the task today and the question today is how can we use the robot learn this kind of interactive skills so they can also interact like humans and they can open the drawer, they can open the laptop, they can twist the bottle, and so on and so forth. So, but looking back to some previous examples or videos, we can find that actually robot can do a lot of damage to the world and to itself. And we back to the challenge because a lot of annoying train the robots will work and the dogs can crash themselves. So it's really expensive to retrain this bot in there. And solution, today we are using a lot of simulation to train robots, and here is more like cheap and more expensive solutions to train this robot in the simulations. So for example, we can teach them manipulation skills, and we can use the RL methodology to scale up training, scale up the learning, and also the verifications. So training will be much cheaper than training the robot in the real world. Basically, researchers are using the simulators like Majuco and use as a sim, so that we can use the synthetic assets and train skills by trainings. And however, look through today's techniques, we have still find a lot of challenges remaining. The core problem is, as we align with the topic today, is that we're actually in lack of high quality, realistic, and interactive articulated objects. So previously, we have two methods to collect this kind of 3D assets. And one of the way is to create the synthetic assets. For example, from the CPN, from the GAPRNet, we can manually create a lot of related objects with articulated parts, axes, centers, different like articulation parameters. However, this kind of creation is very labor intensive. So see every annotators, we need to annotate the part in the segment 3D objects, we need to find the centers, the axes. So we cannot scaling up this kind of 3D assets in a large scale. And another way of creating is by scaling the objects from the real world. However, it still needs a process and post-process for scanning this kind of high quality assets. So, okay, I cannot touch them. Awesome. Another one?
You can have an powerful. There's some.
for this function to be enabled, I think. Oh, currently it's on duplicate. Sorry, wrong. Maybe it's maybe change that. Including Q&A, yes. Okay, or something. So another way of obtaining kind of asset is to the real-world scanners to scan articulated objects, and still has a lot of post-process. So what I want to talk about today is how can we automatically like get this kind of large-scale articulated assets. And talking with my student, one of my students, with an interesting fact is that current stage models, especially for the articulated one. So basically, for some high quality assets, you might need like $100 for each of these three objects. So it's too expensive. We cannot afford it on the activity. So a very natural way of addressing this problem is that we can learn from the real world interactions, and we can use the reconstruction technologies, we can use the generation technologies to create a large scale 3D apps without too much annotations, right? So this comes with today's one of our papers on RGS, which was published at actually this year. So the basic idea of RGS is that we can use the 3D Gaussian and efficient representations reconstructing the articulated objects so that we can save us money by use the RGBD input and use the Gaussian spelling to reconstruct very quality 3D. So in case you're very familiar with Gaussian mapping, so here's preliminary introductions about Gaussian mapping. Is a neural representation of 3D things. So basically, we are representing the 3D certain parameters for descriptions, including scale, quaternion, spherical harmonics coefficients. So this parameter defines equations. And using the equation below, we can render, or we can say we can spline the Gaussians into the images, and we can do the rendering. And here is a brief comparison with the neural network that some of you may be familiar with this. So basically, neural networks, they are array-based rendering techniques. You have different arrays from spaces. You have parameters like density, position, and directions. This the property of each race. And you can use the rendering technique to project this race into the RGB image to do the rendering. Compared to the neural network, Gaussian splatting are different kinds of Gaussians and then we can do the rendering. So one of them is rendering, and another one is the Gaussian. And with Gaussian-based, Gaussian rendering is more convenient to combine the Gaussian splatting, the rendering technique with the reconstruction technology. For example, we can use the structural motion as the realizations. So we can get the camera pose and we can get the initialization of Gaussian space, and then we do the projection to the differentiable realizations. So we can render these 3D Gaussian points to the image space and get the RGB image. So using the Gaussian, considering what is the most natural step for reconstructing the articulated objects. So basically for defining object, right? For example, the fridge, if it has open and close. And basically, you have two states defining each of part articulations. We choose the most intuitive step, which is trying to recover the articulated object from the two states. So basically, we have two states as the input, state 0 and state 1. And each of these consists of multi-view RGB images. So we can reconstruct the 3D object from state input. And say the RGS is trying to cover two things. And one of the thing is canonical Gaussians, which define default reconstruction or default geometry, default states of the 3D objects. And then we can ask the articulation models. For example, you have some schematic or relative joints, and you can define some parameters we call the articulation model based on the articulation type. And then we can use the deformations applied to the 3D Gaussians, have the deformed 3D Gaussians, and we can render 3D Gaussian to different states to render, right? And then we can use the two input, the canonical Gaussian and also the articulation models. So we can do a different type of articulation to the object. So we get a digital replica of 3D object we get our daily life. And in terms of solving this problem, we find it's very challenging to optimize things together. Certainly, we have object geometry, which is very complex if you have multiple parts, right? And then we should do the part segmentations. And we have the articulation parameters, which is included in the articulation models. And it's really hard to disentangle factors since we only have the two states as the input. Ideally, we want the feed the results. We want to get the result from the left side. Basically, we have very clear segmentations of each, and then we have very well reconstruction results. The different colors represent different parts, and we have the center of each part. However, during implementations and some initial experiments, we actually found we always get the result from the right side. So basically, we cannot get very clear segmentations, and the reconstruction is not very good. So our problem is how to disentangle the canonical Gaussians, the segmentation, and also the relations from the two input. And during our research, we find this will we find really important to do a good or better visualizations for part models. And we present a four-stage framework for reconstructing the articulated objects. So in the stage one, we train for each stage, we train canonical 3D Gaussians based on the module RGB images. And then we match the two sets of the canonical Gaussians, so we can have the correspondence of each point, which each Gaussian spec. And then we clustering of the dynamic points to initialize power centers. So if we want to do clustering, we have the power centers, and we can assign the Gaussian spread to the centers, right? Eventually, we can get a canonical Gaussian by taking average of the two Gaussian states. And here is a brief illustration of how we do the center-based part assignment. Basically, we use the knowledge distance to calculate the distance between the Gaussian stats and also the centers. For example, you have n Gaussian stats, you have k centers. So basically, you can have a matrix on the weight matrix, and you use that to vote the centers. So you can assign Gaussian stats to each part centers. And after getting centers, the canonical Gaussians, and then we do the optimization, right? We want the geometry, want the articulation parameters. And the way we do it is that we use a very common practice in reconstruction called analysis by synthesis. So basically, we reconstruct the 3D for each state, and we render the 3D Gaussian, we render the RGB image, then we can get the depth. We use the render loss, including the image base loss and also the transfer distance, the depth render loss, to compare the rendered RGB images with previous RGB image input. So this would be a very good correspondence or consistency between the reconstruction and the input. And we pair with some previous models in terms of the quality of reconstructions. And as we can find out that compared to like DKA, we have a better part reconstruction result with the correct activation parameters. So we visualize the object by rotating certain part or translating part. And here is the comparisons. We use the measures like axis angles, images, distance, and we get some performance on objects. And after RGS, we're still thinking about how to push the access in a better way. Checking through all the we still find there's some remaining problem. So taking this examples, so this is a cabinet with multiple parts. So for models, it's very hard to segment each part. So initially we have one part. It's really hard for models to segment them and get a optimized 3D motion. So it's very important for us to do a better segmentation as the initializations for the model. So based on that, you need a very good initialized segmentation models. Otherwise, the optimization will be very hard because you need to find out, you need to optimize the numbers of the part, which is the most for the regression problem. So that we can use models like SAM to get a better segmentations. And another problem is that exists a lot of ambiguities if we only have the two states as here's an example. The left is the input image, and we initialize the Gaussian according to the states settings. However, since the two doors are open at the same time, so the model might be very confused, like are they grouped together? They're on the same part or they're from the two parts. So it's really hard to distinguish the parts if you only have two states as input. So a very natural way to address this problem is that we can extend to multiple state. The most simple way is we can use the video RGB video as input. So we can watch it from the video and with more information, including the photo motions, and we use that as the motion information for better interest, including segmentation, including the other properties. So according to this video, we have another papers and just put it on the app called Video RGS. So it's basically a step forward towards RGS. We're trying to use the video as a natural video as the input to reconstruct 3D objects. And task is becoming more challenging because you have more information as the input. And using pure video vision is very ambiguous for the articulation learning. The main problem is that we have a lot of factors. For example, to recover the camera parameters, we don't restrict the camera parameters. We are using free camera views to capture the 3D objects. We need to recover the poses and then to again reconstruct the camera object geometries. Also, the part segmentation I mentioned before, which is very critical for complex objects, has multiple parts. And we need to cover the articulation dynamics, the rubber and prismatic joints to ask parameters. So video input actually entangle these factors together into a. So you really need to recover a lot of information. So our method, in our papers, we found out it's really important to leverage the motion product, to leverage the vision tech, so that we can have a better instruction the reconstructions. So here is that we use a 3D tracking model to provide better in-transition reconstruction. And from the left side, we can see here is the motion tracking result from an RGB video of the 3D object. And here we can see that we can recover the noise, we can recover that information, and we can estimate the flow. So basically for situations like prismatic or revolution joints, we can parameters according to the motion information. So this might be a very good way of understanding the 3D object according to the motion flows, and the current technology is pretty good for us to recover certain articulation parameters. And here is an entire framework or pipeline of our RGS models. So we have a sequence of RGB image as the video input, and then we use the off-the-shelf camera arms and camera pose can be pretty good, but not perfect. And then the critical part comes. So we use the 3D tracking technology, so we can have the 3D checklists and track the 3D points along with the videos. And then we can use motion analysis models, and we can do syntactical static part, and the noise part, and prismatic and revolute part. So we can estimate damages. And after that, we can do a better initializations. For example, we can have better classroom techniques and better mental reconstructions and part segmentations. Using the initialization with the canonical Gaussians, we can do the optimizations like before. So first we have canonical Gaussians, and then we have the deformation field, which is repeated RGB images and also the data with the original input and all the estimate. So we use the supervision for our models across the entire video. And compared with the previous method, we find the result of video RGI is really impressive. Of course, we of our paper and our models nowadays. However, that can reduce the error by up to 2 orders of magnitude. So this means that we have good generalizations, including the segmentation and motion models of videos. We can reconstruct the articulated objects in a near perfect way. And we do a lot of ablations. So we want to discover or understand why the performance is improved in a grayscale. So we apply the motion and also the initialization method. And the result actually that the motion prior technology, and also the center deformation initialization, they are very important to the result. So they with more advanced technology and motion analysis, we have better innovations, so that helps the reconstruction of the articulated objects. And we do some quantitative comparisons with previous models. And as we can see, the part segmentations and also the part numbers, the entire geometries can be covered in a very good way compared with the previous models. And we want to explore how well is the model can be generated in our settings. So actually we capture some views from offices, and we holding the camera around us on the coffee machine, the table, and actually we have pretty good and stable results of the object geometry reconstruction, also the articulation reconstruction. The red axis is like rotational axis, and here are some part percentage results. And we are also developing some like applications on iPhones. We can capture the video using iPhone and reconstructing this kind of 3D assets and do as a simulation properties. So here is some recent progress in the reconstruction. And besides beyond reconstruction, we are still thinking about, so for the reconstruction, we still need to build, right? You need to have a lot of video shooting around the objects, and you need to do the interaction with the objects. It's still kind of complex or expensive. So now we want to explore is, can we like automatically scaling up the 3D generation without doing the reconstruction? So the method is generation, right? Today we're talking about a lot of generation models. So we're thinking about, can we like using RGB image as input, and then we can automatically generate 3D articulation assets. So we have a paper published in Signal of Asia this year. So the idea is that we want to leverage the video diffusion model, and then we generate the articulated objects with a single RGB input. So here's a video showing that that is the RGB input is pretty cool, and the left side is the results, so that we can generate articulate 3D assets in different parts and also the articulations. And here is an overview of the dream art. So basically, it's 3 stages. In the first stage, we want to do the 3D object generation phase based on the RGB input. Basically, we are doing the mesh generations, and we want to segment parts. And for each part, we have the separate mesh. And then we want to do the mesh completions because for some of our SOTA generative models, the inherent or internal structure is not clear. So basically model the surfaces, not modeling the internal structures. We are still need to do some hard mesh completion, and correspondingly we do the image engine, the model image from different views. And the second stage, we want to leverage the video diffusion model to really get different views of the RGB image as the supervision for the articulation parameter reconstruction. So we have the input image, we have the visible map, and we have the model and model part. And we want to use them as the input for the vision model. And we want to have the supervision of different views of RGB images, like this, multi-view, multi renderings. And we can use data set like ability to generate the correspondence RGB image, the input, and also the output. So by fine-tuning a video diffusion models, we can create the multi-state renderings of the 3D objects. So they can provide the solutions for the 3D asset areas similar to the construction process. So in the stage 3, we just animate the joints and also the textures based on this kind of input. And basically we can render the 3D assets into different views, right? We can verify the correspondence. And then we can parameterize the meshes. We can parameterize the textures, geometries, so we can do joint optimizations based on all these kind of inputs. So now let's go. Basically, the RGB images, and then we can regenerate some high quality 3D assets, have calculations, the parts, and also we can do animations in simulations. And beyond this, we can do scene level analysis, scene level generations. Basically, we can compose the 3D objects into a scene, and then you have different object categories. You have different groups of analysis rooms. Compared with the previous one we have, we also get pretty results. The generation result is much clearer and exponential models, and also the segmentation and articulation is better than previous models. So next, we have talked about the reconstruction, also the generation process to scale up the single object generation, right? Single asset creation, and this is topic of our workshop today. And next is the level. So basically, we want to train the robots to have a really good environment and the 3D world play these things in the production. So in one of our recent works, causing bloopers with an arrow presentation of this workshop, and you will see the author doing the presentation later. So in this work, we're trying to have an agent. The agent can use an input. You can have the requirements of your thing. For example, the functions have one G, one application. With the engine to just requirements in real-time fashion, so the model can generate results and can add it, also add the 3D. So using we can get a very good the whole 3D rather than that is go if we a complete generation of the syndrome of the building, then we can put the simulation environment of the or for the matricle, and then we have reach object interactions. We can have artificial interaction like we did before, and then we can train robot information, compare training to, and also do some randomizations that can be applied on the same tutorial. And we currently have a lot of technology. So this could be a very good pipeline for creating a large scale 3D assets and training the robot from zero. So, so that's the measurement of the talk. And here are takeaways. So they are measuring mostly how to advance the articulated object generation perspective, reduction and animation. We want to do it in a very efficient, so in a very good way, so we don't need too much cost to build the and scale the very good way. And we find the solutions using big input, we using the slowdown of the shell technologies and reduce reconstruction result of the 3D articulated objects. We decided to ask the artist to design every single piece 3D object. And throughout the RGS and also the video RGS, a clear message is that motion prior and better implementations are most critical for the reconstructability implementations to analyze to provide a better insurance for the 3D object constructions. And also we want to the generations are into room level, scene level simulation, so we can support that. And lastly, simulation, the work environment. Thank you.
Does anyone have comments? Or to define for the BGT for the reconstruction of the camera rolls. Usually, it seems like the scene will have a lot of noise if there are high motion.
Yeah.
Have you
and we still want the background or the and out using the vision technologies. So this is the term for the standardization of the assessment.
Hi, that's work. I wonder for the ocean platform, what exactly the data you is just the strategy or you have specific metrics for specific role?
So, what kind of motion models we are using?
Yeah. What is the problem for that?
So the prior is out models for the validity and also the capacity. So this kind we the prior models.
Okay, so it's not the prior of the robotics, the prior of
Yeah, it's the prior of the motion part.
okay, thank you.
I think
I think
the time
sorry, you can ask me like after this.
and the round of applause for Sue.